So, good morning, students. So, today we shall be studying another a little bit of important concept, which is important in exams and entrance point of view. So, you need to understand the concept and the formula. You can also derive there if you do not remember, and they are quite derivable, which will consume very less time if you do it correctly. Okay, let us now start the topic. So, what is today's topic? We will be needing a ruler, electric field. Continue with me due to a thin spherical shell. And there are many things after this we are going to derive. So, it is today's topic is electric field due to a thin spherical cell. So, what is a cell? Okay, or what is a spherical cell? You have seen a balloon. Okay, you have seen a balloon, though we can neglect it now when it is inflated, that is we pump air into it. Though the skin is very thin, but we cannot neglect it. Okay, so it is a cell. That thing is a cell. So a cell is like this, a spherical cell is like this, an object whose inside is hollow and has a very thin skin or very small thickness. Okay, a very small thickness, and this thing is hollow. This thing is hollow. The inside of thing is hollow, and this is very small. The thickness is very small. Okay, so this is a spherical cell. So we are now going to find the electric field due to a thin spherical cell which is uniformly charged. Okay, you can include here uniformly charged. It is very important to include such things because these are very small things which need to be included in your introduction. So you have been given a thin spherical cell which is uniformly charged. Now just we are going to do a diagram. So this is your cell. You can just put up a sphere, try to build, try to construct something like this. Okay, this is a sphere, and try to construct a cell around it. Okay, do not think this is empty. Okay, this is its thickness, like in a balloon. You've seen a balloon. So a balloon is like this. You inflate it with air, and this is a cell. Okay, you cannot ignore its thickness. Now let us draw some other things. You can actually see that uniformly charged. So since it is a surface, so the surface charge, so you are going to be using surface charge density. So this is uniformly charged. Okay, so let us now write, let us write with me, let us consider a uniformly charged, a uniformly charged, yes, the recording is being going on. Let us consider a uniformly charged thin spherical cell, spherical cell with charged, sorry, surface charge density. Just include these things. These are very small things, but they are important. With surface charge density sigma. Okay, the surface charge density is sigma. So far so good. we have considered as uniformly charged thin spherical cell whose surface charge density is sigma. Now let R be its radius. So what is R? This is O, that is the having center O, having center at O. So O is the center of the spherical cell. You can name it here, and R is its radius. The inner thing, okay, the inner thing is the radius, not this much, because this is very small. Okay, we are just trying to show you here, and it is very small. Okay, so now as you can see, it is spherically symmetric. Okay, the charge distribution is spherically symmetric. That means E is radial. The direction of electric field is radial, as you have learned from other things. When in a sphere, or when a charged sphere is given to you, or when a point charge is given to you, you have learned that the field is radial. So since, write like this, since it is a spherically symmetric distribution, spherically symmetric distribution, E is radial. E is radial. So the direction of E is radial, or E points out radially outward. Now, and let what will be the magnitude of E? So since it is radial, and you can write, and its magnitude, it is not necessary to include these things, just you can write, and it's to understand, and its magnitude is same at points equidistant from O, equidistant from O. So if there is a point P, it is a point Q, it is a point R, if they are equidistant from O, then that means electric field at this point, at this point, and at this point, they are the same. The magnitude of electric field at this point, or that at PQR point, if it is a PQS, okay, we have included R here. So at point P, at point Q, and at point S, the electric field is same. When is that possible? If they are equidistant from center. That means P is located at the same distance as Q is located and S is located. Okay, so just let us now just rub them. We don't require them now. So E is radial and its magnitude is same at point equidistance from O. Now, what is your work? We need to find electric field at point P, which at a distance R from O. So P is any point. At that point we shall be calculating electric field, and it is at a distance R from O. Okay. So now we shall be needing a ruler. So whatever we have written here, we are going to show it here. Like E is, if you draw E like this, see the direction of E is, or it is radial. Okay, it is radial. You can actually see that it is radial. So let me first complete my drawing. So this is the direction of P, this is the direction of P, this is the direction of P at these points. So these are not necessary to mention, but in exam, but you can, to understand, you can just write them like this. So at this point also E is like this. Okay. Now P is any point. So P is a point. So it has asked that P is a point which is at a distance r from O. So what is the value of r? We don't know. So we need to find out a generalized form. Okay. P can be here, P can be on the surface, and P can be on the inside of the spherical cell. So it can be anywhere. So we need to find a generalized equation or generalized solution for this problem. So at first we are going to calculate P at outside the spherical cell, and after that we are going to calculate the electric field P which is on the surface, and at last we shall be calculating electric field E at point P which is situated inside the surface. Okay, so now let us start it, and it is charged with um, surface charge density sigma. So you can mark point 1 when r is greater than r. You can write like this, or in bracket you can write P is outside spherical cell. P is outside spherical cell. When P is your outside spherical cell, you can see that this distance is r, and you can actually see that this is r, and your r is greater than r. So this is your first point. Okay, at such points you are going to calculate your electric field. Okay, so to calculate electric field, since it is a spherically symmetric charge distribution, we can actually use Gauss law. In order to use Gauss law, you need to consider a Gaussian surface. Let us consider a Gaussian surface. So what is that Gaussian surface? It is a sphere. Okay, it is a sphere. Gaussian surface, a sphere of radius r. This is your Gaussian surface, and it is of radius r. So you can actually draw a Gaussian surface like this. So it is your Gaussian surface. Try to make it symmetric. It will be more beautiful. So let us consider a Gaussian surface of radius r. Okay. So why do we consider Gaussian surface? So that we can actually calculate the electric flux through that surface. Okay. So if sigma equal to surface charge density, not required now. We can actually, okay, if sigma equal to surface charge density. So what is the total charge? What is the total charge on that spherical cell? So total charge Q is equal to sigma into area of that object. So what is it? It is a spherical cell. So actually it is a sphere. So the surface area of sphere is sigma into 4 pi r squared. Okay, sigma into 4 pi r squared. This is the total charge in this spherical cell. So just understand that Q is equal to sigma into 4 pi r squared. Okay, this is what you need to be considering. Okay, so let us now rub this thing and write it on the side. Okay, we don't need it to be at the center. So what is Q? Total charge Q is equal to sigma into 4 pi r square, where r is the radius of the spherical cell. Okay, r is the radius of the spherical cell. Now, as we have considered a Gaussian surface of radius pr, then we can see that actually it encloses the total charge on the spherical cell. It encloses charge Q. It encloses charge Q, and we have found out Q. Now, electric flux, since it is a closed surface, electric flux, you can apply full stop here, electric flux through this surface. So what is the value of electric flux through this surface? That is phi E equal to E into 4 pi r squared. Okay, it is 4 pi r squared, because you can see that the value of electric field at P is E, and what is the surface area of the Gaussian sphere, where we shall be considering the surface area of the Gaussian sphere, it is 4 pi r square, because r is the radius of the Gaussian sphere. This is our r. Okay. Now, what is the value of E? E is equal to phi E by 4 pi r square. Okay, it is E equal to phi E by 4 pi r square. Now, you can also calculate electric flux from Gauss theorem, that is phi E equal to Q by epsilon naught. As we know from Gauss theorem, it is your Gauss theorem, phi is equal to Q by epsilon naught. And if it is equation 1, you can actually put phi E there. Now, putting phi E in equation 1, we get, so what will you be getting? E equal to phi, put Q by epsilon naught, in case of phi, 4 pi epsilon naught r square, and when you rearrange them, you will get 1 by 4 pi epsilon naught Q by r square, Q by r square. This is the value of electric field. This is the value of electric field. So you can see that it is quite similar to the general electric field for a point charge distribution. So it is equal to the general field. So you can see that we can actually put Q, the total amount of charge on the spherical shell, at the center, and just calculate the value of electric field at point P, which is at a distance r from the center. Okay, so you can now put the value of Q. So as you have calculated earlier, that is, since Q is not given to you, you have been given sigma, you have been given r, that is capital R, and you have been given small r. Okay, so you can actually put into 4 pi r squared divided by 4 pi epsilon naught r squared. So sometimes it is easy to remember and sometimes it is easy to remember. So you can actually cancel 4 pi and you will be remaining with sigma by epsilon naught r by r whole square. By r whole square. And this is the value of electric field at a point P, which is actually outside the spherical shell. And this is what you need to remember. You can remember it like this, you can remember it like this, no problem. Now if you remember like this, you have to find the value of Q if this data is given to you. If this data is given to you, you can actually find it like this. Or if you don't want to find like this and you want to calculate using the actual terms given, you can actually use this formula. So at last I will be writing, that is 1 by 4 pi epsilon naught, that is our traditional method, and which is equal to sigma by epsilon naught r by r whole square. So this is the value of electric field. You can actually remember it like this or remember it like this. There is no problem in any of the method. Okay, so there is no problem in any of the method. So you can actually remember it like this and find the value of Q from the start. At this point you can find the value of Q initially and then put these things here. So this was our first case when R is greater than R. Okay, this was our first case. Now we shall be writing our second case. So let me just rub these things. The second point can be also calculated at this point, at this phase, that is when P is on the surface, when R is equal to R. Okay, it is exactly on the surface. P is exactly on the surface. So when P is exactly on the surface, you can actually imagine a Gaussian surface of radius capital R, or a radius of capital R, which encloses charge Q. So what should be it like this? And we apply Gauss theorem here. Apply Gauss theorem. So in order to do this, you have to consider that your Gaussian surface, spherical surface, is of radius R, which is equal to capital R. Okay, at R is equal to capital R. This is what your condition is. So from Gaussian theorem, you can write E into 4 pi R squared. So Gaussian surface has a sphere of radius capital R. So E into 4 pi R square. Its surface area is 4 pi R square actually, and you can write Q by epsilon naught. The total, the LHS is the flux and the RH is also the flux. You can write here phi equal to E into 4 pi R square is equal to Q by epsilon naught. So the important thing is that you need to find E at this point. So what is E? Just take this thing to the right hand side. You will see that 1 by 4 pi epsilon naught, after rearranging, you will get Q by R squared. This is the value of electric field at this point. Now put the value of Q. What is the value of Q? That is 1 by 4 pi epsilon naught. What is the value of Q? That is sigma into 4 pi R squared by R squared. You have just replaced Q by sigma into 4 pi R squared. So what would be E? E would be 4 pi gets cancelled, R squared get cancelled, sigma by epsilon naught. Sigma by epsilon naught. When? This is when your R is equal to R. So P is on the surface and P is on the surface and you consider a Gaussian surface of radius capital R. You have a Gaussian surface of radius capital R which encloses the total charge Q, and you calculate flux like this: E into 4 pi R squared is equal to Q by epsilon naught, and you actually find E, that is 1 by 4 pi epsilon naught Q by capital R squared. So you see that it is only equal to sigma by epsilon naught. And previously you have also learned that for a flat sheet, for a uniformly charged flat sheet, you have learned that the value of electric field is sigma by 2 epsilon naught. It is quite similar to that. Okay. So this was the point when P is at the surface. Now the important point comes that when our considering point P is inside that spherical surface. Okay, let me rub these things. I don't have space now, so I have to rub these things. So please wait. For this point, we shall be considering another diagram, but before that, we need to write it like R is less than R. That means P is inside the cell. Inside the cell. In the first point, P was outside the cell, and the second point, P was on the surface, and in the third point, P is inside the cell. Okay. So for this, we need to draw another diagram. That is, just draw a cell. You need to do it in a bigger scale now to understand these things, or to fit the diagram. So draw a cell. So you can actually ask that why that we are building a bigger cell now. So I shall be answering that we need to fit a diagram. Okay, we need to understand the diagram in a very good manner. Okay, so this is a diagram. This is your cell. You can actually build the cell like this, okay, and point out electric field like that or that. We don't need that actually. Now, since P is inside it, okay, this is your radius R, this is O, this is your radius R to the outside or in the inside, or to the, oh sorry, in the inside, and P is a point here that has a radius R, okay, that has a radius. You can actually draw a smaller O. So P is inside the cell as it is been shown. So here also P is inside the cell, at a distance R, at a distance small r, okay, at a distance small r. Okay, we consider a Gaussian surface, So actually it is a spherical Gaussian surface. I am missing spherical very much, so I am including it later. So we consider a Gaussian surface of radius r, around O. O be the center, and we need to consider a Gaussian surface of radius r. So let us draw that Gaussian surface. You can actually draw a Gaussian surface by dotted lines, okay. Since it is an imaginary thing, you can actually draw a dotted line, okay. So what should be the charge enclosed? Okay, the total charge is enclosed, or the total charge is contained in this ring, okay, in this thing. So you can actually see that there is no charge inside it. You can actually see there is no charge inside it. So it encloses zero charge, or no charge is enclosed by it. So in this case you can write actually Q is equal to 0. Now by Gauss theorem, what is the flux through this surface? Phi E is equal to E. So E is like this, E into 4 pi r square is equal to Q by epsilon naught. These are the consequences of our Gauss theorem. So now find E equal to 1 by 4 pi epsilon naught Q by r squared. But Q is equal to 0. Net charge or charge enclosed by this Gaussian surface is 0. So you get E is equal to 0. Inside the cell, so include this important point, inside the cell there is no electric field. Inside the cell there is no electric field, okay. This is what about electric field due to a thin spherical cell that is uniformly charged. And you have reached the conclusion of this question, and still a thing remains, so I shall be describing now. So let us now write the formula which we have derived from these 3 points. So the formula are, let me take some time to rub this. So what are the formula? We don't even need these things. So for point 1 we got E equal to 1 by 4 pi epsilon naught Q by r squared, okay. It was outside the cell, okay. So you can write the condition sideways. What is 2? E is equal to sigma by epsilon naught, okay. Now 3, is equal to 0. R is less than R. When point is inside the cell, at whatever point inside the cell, the electric field is 0. Now we need to graph it. Okay, we need to graph it, or we need to show the dependence of E on R. We need to show the dependence of E, electric field, on R. As we have seen that we have found different things for the uniformly charged spherical cell. Okay, thin spherical cell. So what should be that graph? So the graph is like this. This is y-axis, this is x-axis. So on the y-axis you are going to plot E, and on the x-axis you are going to plot R. So it is like this. Now you can actually draw a spherical cell, or just draw a sphere. Okay, just draw a sphere here to understand it visually. So let me draw a better sphere. Yes, it is a better sphere now. Here R is equal to 0, here R is equal to R, and here R. Okay, this is your at this point R is equal to R. So what is the value of electric field? Since you have seen that inside all these points electric field is 0, there is no electric field at these points. But at point R, you have found the electric field like this, sigma by epsilon naught. So at this point, we can draw a point like this. Sorry. Let me take the ruler. It will be better. So at this point, draw it like this. Since electric field is 0 in the inside points, so draw it like this. There is no electric field at all of these points, but the value of electric field at point R is sigma by epsilon naught. This is, you have to draw dotted. Okay, you have to draw dotted because electric field is 0 at this point. E is equal to 0. And remember this graph, you can be asked. So what is the value of electric field at this point? That is E is equal to sigma by epsilon naught, or 1 by 4 pi epsilon naught q by r squared, capital R squared. Okay, so it is also, you can actually write like this, or 1 by 4 pi epsilon naught q by r squared. Okay, when r is equal to r, you can actually write like this, and from that point onwards it is like this. It is like this. So what is the dependence of E on R? E is inversely proportional to R squared at all the points where R is greater than R. Okay, at this curve, in this curve, the dependence of electric field on R is E is inversely proportional to square of the distance R. Okay, so it goes like this. You have to remember this thing. You have to remember this thing. This is an important graph. So you need to do it dotted. So I think that you have understood these things. So this is electric field at this point. You can draw it like this. Okay, not extend these things. The value of electric field at this point is this. So I assume that you have understood these things, and now I am going to conclude my lecture. So if any doubt arises, you just mention it in the comments of the video. I will give a good response. I will provide you a response in the upcoming lectures, or in the comments itself. So if you feel there is any part missing, you can actually put a mail or drop a mail at the given uh, mail which I have described in the which I have given in the description box. So so far so good. We have learned the electric field due to a thin spherical cell. So these lectures are going to be long. So since we are going to be in a detailed manner, so don't worry. Just learn things easily, and once you learn these things take a place in your brain. Okay, you can't delete in you can't delete this from your memory, which is quite helpful to crack entrance exam. So up until then, take care, practice more, and see you.